Chapter 5, Day 1, we're going to determine whether a function is in fact a linear function. And we're going to look at it in terms of its table, graph, or an equation. So there's three ways that we can determine whether something is linear from its graph, equation, or a list of ordered pairs or a table. So from its graph, it should form a straight line. So when you look at linear, it has the word line in it. So keep that in mind. So here's the definition of a linear function. There's a few different features, but remember, a function in general means that each x value has to be paired with exactly one y value only. So what makes a linear a special function is the graph is a straight, non-vertical line. Remember, it can't be vertical, okay? Remember, we can't have a vertical line like that because that's not even a function. So in order for it to be a linear function, it has to be past the function test. Okay, so when we say straight, okay, it has to be going in the same direction as well. So in other words, if we had a straight line and then it came back up that way, that is also not a linear function. So this one is not in the same direction. Well, we have some non-examples of that. So we can have a line that is increasing. This function is increasing when we look at it from left to right. Or it could be decreasing, or it could be what we call constant. So if increasing is going up, hopefully you can guess what decreasing would look like. That's going to be going down, left to right. And we always read these graphs left to right. And a constant doesn't go up or down. It's just a straight horizontal line. And this all has to do with what we'll get into a little bit later is the slopes or the rate of change. And I know some of these things might be familiar to you, but we're going to review and make sure that we understand what all of these pieces of a linear look like. So here's some non-examples of linear. So the reason these are not linear is because this one right here is not even a function. Because it doesn't pass the vertical line test right here. Okay, you can touch many points when you draw that vertical line. This one is not straight, it's curved. And same with this one. It's also curved, and this is again not in the same direction. It's important sometimes to look at what something is, but to really understand it, to look at what it is not. Okay, so let's practice this. Let's determine whether or not this function is in fact a linear function. Okay, these pass the vertical line test, so we know they're already functions. It is a function, okay, it is a function because it passes the vertical line test. And we could just write, passes the vertical line test. Is it linear? Okay, that's what we need to decide. If it's a function now, in fact, is it linear? And this one is no. Why not? Because it's curved or not straight. How about the next one? Same reason. No. Curved. All right? So that gives you a little bit of understanding and practice. Okay? Now you take a turn, okay? I want you to try these two examples, determine whether or not it's a function, and if it is a function, determine if it's linear or not, and then pause the video, do these two examples, and then restart the video to see if you got it correct. Okay, so this is a function, This is a function, yes, because again, it passes the vertical line test. Both of these are in fact functions because again, they passes the vertical line test. Okay, this first one though is not a function because the line is not going in the same direction. So it's not straight going in the same direction. Okay, and the second one is linear because it is a straight line going in the same direction. All right, take a look at these two. See if you can try these two now. Pause the video and then restart the video to determine if you got it correct or not. Okay, this first one is a function because even though this looks like, oh, it might touch twice, this is going to keep going very slowly, but it's going to go out very slowly. So this is a function, and so is this. They are both functions, again, because it passes the vertical line test. Now, let's talk about whether or not they're linear. Okay, this first one is not linear because it's curved. And this second one is linear because again, it's straight line, same direction. All right, so hopefully that gives you some information and practice with graphs. So now let's look at from a set of ordered pairs. How can we tell whether it's linear from a set of ordered pairs? We know for a function, it has to have a no repeated x values in order to be a function. But specifically, it has to have a constant difference in the x's and a constant difference in the y's. So there must be a constant increase or decrease in order for it to be a linear function from a set of ordered pairs or a t-table. In both the x and y values. Or we could say the rate of change is constant. So, for example, if we look at this one, notice that there are no repeated x's right here. If we look down this list, there's no repeated x's, so we know it's a function. Same with this one. We can look at the x's, they don't repeat. So now let's look at what makes them linear or not. So this one, you can see that we are decreasing by 1 in the x values, okay? And in the y values, we are decreasing by 3. Every decrease to go to the next number is by 3. So this is an example of a linear because of the constant decrease. This one, if we look at this, we do have our x's have a constant, well, actually they don't have a constant increase. So you might go, oh, well then it's not linear. But we also have to look at the ratio. And I said the rate of change, but maybe a better word here to put in, and I'll go back and put a different color. So maybe you want to change this, is the ratio of the change is constant. So what do we mean by the ratio? Well, we looked at the x's, it's not constant. We look at the y's, here we have, this is going +3, and this is going +9. So when we look at the ratio of change, this is, the x's are going up by 1, and the y's are going up by 3. In this next change, the x's are going up by 3, and the y's are going up by 9, but that is the same as 1/3. So we have a constant, let's try to write that a little bit better, constant ratio. So this ratio right here, 1/3 and 1/3 is a constant ratio, so it's linear. So those are the two things you need to look for when you are determining whether the function is a linear function from a table or a set of ordered pairs. This is a non-example, so again, sometimes that's just as important as when we look at this. So if you look at this, we are going down 1, but then we are going up 1, up 1. So let's look and see if the ratio then is the same. This is going down 3, this is going down 1, this is going up 1, and this is going up 3. So let's look at the ratio. The x's are going down, the y's are going down 3. This next ratio, the x's are going down 1, and the y's are going down 1. Okay, we can see these ratios already are not the same. So not the same ratio, and we don't have a constant change. Increase or decrease, I'll just put change in x's and y's. All right, so let's see if we can do some examples here and practice. So determine whether the set of ordered pairs satisfies a linear function. Again, if we look at the x's, there are no repeats, so we already know it's a function. Sometimes it's helpful, it's not necessary, but it's helpful to put these into a t-table, just because I think it helps you organize your work a little bit better. So I'll go ahead and do that to show you. So now let's look. This is going up 1, up 1, up 1. The y's are going up 5, up 5, up 5. So it's linear because of the constant change in x's and y's. Okay? So first look for a constant change in both the x's and y's, and that will help you figure out if it's linear quickly. And if it's not a constant change, then you look at a constant ratio. All right, so I'll do number 1 and then pause the video and see if you get number 2 correct. So number 1, we have a constant change. They're all going up by +1. Here this is going down 4, and now it is going up 4, and then it's going up 6. No, that's not right. It's going up 4 again, and then it is going up 4, and I'm like, oh, well, that seems odd because it's constant, up 4 to all these other ones. So now I'm going to go back and look, and it's like, oh, wait, from 0 to 4 isn't going down 4, it's going up 4. So yes, I have determined that this is a function because of the constant change in x's and y's. Okay, pause the video, see if you can figure out number 2. All right, let's look and see if you got it correct. We can see that we are going down 1, we're going down 1, we're going up 1, and we are going down 3. So down 1, actually this is +1, then we are going +1, and then we are going down 3. So not a constant change in x's and y's. So let's look at our y values. From -4 to 1, we are actually adding 5. From 1 to 6, we are adding 5. But from 6 to 7, I'm only adding 1. And from 7 to 12, I'm adding 5 again. So now we need to look at that ratio. So again, I'm going to go back and check because I have plus 5, plus 5, plus 5. But I'm going to double back and look and see, does 6 to 7, did I make a mistake? No, I did not in this case. So now I'm going to go back and look at the ratios. So I have the x's are going down 1 and the y's are going up 5. In the next example, it's going up 1 and up 5. So 1/5. But now we have 1 over 1, and then we have down 3 and up 5. So we do not have a linear function, okay? Not a constant ratio. Oh, I misspoke here, and these should all be my determination of linear or not. Okay, and I'm saying no. Okay, this is not linear because not a constant change or ratio. Okay, if we want to look at whether it's a function or not, they both are functions because, well, actually, this is not even a function because there are repeated x's. So, not a function, so I really wouldn't have even had to go through all of the linear stuff because if it's not a function, it's not going to be linear. Okay, here's 2 more examples. Let's have you determine whether it's a function or not and linear or not. Pause the video, try these 2 questions, and then restart the video to see if you got it correct. Okay, if we look at this one, scan the x's, okay? It is a function, yes, because there are no repeated x's. So we'll just put no repeats. But we'll go ahead and put x's in there. Okay, the second one, if you look at this, okay, there are also no repeats. So there, in fact, this one again is a function. Okay, so no repeated x's for either one. So now let's determine whether it's linear. So let's look at the difference. Okay, hopefully you see that these are all plus 2. Okay, but double check. Okay, don't just assume. And then let's look at the y's. Here we are going down 6. And we are going down 6. And down 6. And down 6. So this is linear because you have a constant change in the x's and y's. How about the second one? Did you get this one correct? Well, we are going down 1, we are going down 1, we are going up 1, and we are going up 1. So we don't have a constant change, so let's look at a constant ratio. This is going up 1. This is going up 3. This is going up 5 and 7. Notice you have a pattern, but if you look at the ratio, let's look at the ratio. We have the change in x's over the change in y's gives you -1 over 1. In this next one, it gives you -1 over 3. I can stop. No, okay? Not a constant ratio, or the ratios are not the same. So we could say not a constant change or ratios equal. All right. Now let's go to our last piece, which is determining whether it's a function from its equation. So here's what needs to happen. You can have no exponent other than 1. In other words, x can only be to the first power. There can be no variable in the denominator. There can be no variables under the radical, and no variables multiplied by each other. So let's look at these, each one, a little bit more closely. And let's have you sort of fill in the blanks, and we'll fill in an example of what that would not look like. So it's a equation if there are no exponents other than the exponent of 1, because this is really 3x plus 8, okay? So what would not be example, okay, so let me get a different color here. So So not like x squared plus 3 equals 10, okay? That's where you have, okay, an exponent other than 1. Okay, the other thing is you cannot have x is not in the denominator. So x cannot be in the denominator of a fraction, okay? So what that would look like is this. So not if you had something like 2 over x plus 1 equals 7. Okay, so again, not x in the denominator of a fraction. Next thing we need to look at is x is not under a radical. That's a square root. Okay, so what that would look like is, or what that would be a problem, it would not be something like the square root of x plus 5 equals 9. Okay, so again, you cannot have that variable under a radical and the denominator under the denominator of a fraction, and it cannot be raised to a power other than 1. And then the last thing we need to look for in an equation is we need to look for that x and y are not multiplied together. So all of these are examples of legitimate functions, because notice you have a fraction here, but x is not in the bottom. Okay, x is your numerator right here. These are x's and y's in the same equation, but they're not multiplied together. And all of these variables are to the first power. And so they are all examples of equations that represent linear functions. So let's look at non-examples. Okay, let's look at what's a problem. Well, this first one is a problem because you have x has an exponent other than 1. So this has an exponent other than 1. Okay, what's the problem with the one underneath it? Well, hopefully you can see that there is a variable in the denominator. Okay, next one underneath. Here's the problem. Remember, when letters are next to each other, it applies multiplication, so x and y are multiplied together. You can't have that, okay? That will not be linear when you graph it. I mean, you can have that as an equation, but it's just not a linear function. Okay, let's look at this one. We didn't talk about this at all, but notice that you have a variable as your exponent, okay? Variable cannot be the exponent. And we'll study those later on. And then the last piece, the last piece is this x is under the radical. So variable under the radical. So these are all the things you need to look for when you determine whether something is linear from an equation. So let's see if you can choose which way these equations go, if they're linear or not linear. And rather than rewrite them all, I'm just going to draw arrows. I'm going to do the first one, okay? This one right here is not linear. Why? Because of this x in the denominator of fraction, okay? I'll do the second one. X is to the first power, so this is actually, yes, this is linear. Now you try the next two, pause the video and see if you got them correct. All right, both of the next ones are in fact linear, so they would go over into linear, okay? If you look at this right here, your x variables right here, there's no problems with them. Okay, this is x to the first power. We don't have x and y multiplied together. We don't have them under a radical. We don't have any variables as a denominator. So you try these four right here, pause the video, and then see if you get them in the correct column. Then restart the video to see if you got them correct. Okay, this belongs over here with linear, and that is the only one. The rest of these belong as not linear, and hopefully you can understand and see why. But if not, I will explain the problems. This one is a problem because x and y are multiplied together. This one is a problem because there's a variable as a denominator, and this is a problem because you have an exponent other than 1. All right, here is an actual real-world example that represents a linear function. So I'm going to actually just go through this with you. A video rental store charges $6 membership fee and $3 for each video rented. We want to find their total revenue after a certain number of videos that they made. So we can make a table of values, okay? If they rent one video, 2 videos, 3 videos, 4 videos, what is this is the number of videos, because remember that is our independent variable, the number of videos, and our dependent variable is the cost or revenue. The cost they make, their revenue, depends on the number of videos rented. So how much would they make renting one video? Well, you might say, oh, they make $3, but remember, they already charged the customer $6 for the membership fee, so they actually make $9. What about 2 videos? They don't make $18 total. They make 6 plus 3 plus 3, or they make $12. For 3 videos, they make 3 plus 3 plus 3, or 9 plus 6, 15. One more video gives them another $3, or 18. So if you look at this, okay, you can see that there is a constant change in the x's of going up by 1, and a constant change in the y values, which you're going up by 3. So that represents linear from a table. The equation we would use for this to calculate the total revenue or cost would be, you would take the number of videos, x, times $3 that you make for each one when you rent them, and then you add that membership fee just once. And if we graph it, this is the number of videos that you rent or that are rented, and this is the cost or revenue that they receive. And here we'll go with 0, 1, 2, 3, 4, etc. And here we'll go maybe up by 2s, 2, 4, 6, 8, 10, 12, 14, 16, 18. I'll skip a little bit. There we go. Okay, so we graph this. One video, they earn $9. So that would be right here. Okay, 2 videos, they earn $12. 3 videos, $15. And 4 videos, $18. So here's what our graph looks like right now. If you think about back to 0, they actually make 0, for 0 videos, they still have made that membership fee. Now, do you connect this or not? Is this discrete or continuous? Let's think about that. Is it countable? Can you count the number of videos? Yes. Would you be able to rent 1.1 videos to have something in between 1 and 2 here? No. So this is discrete. You leave it separate. So is this linear? Yes. How do we know? We can say constant change, straight line. Even though it's not connected, it would still be straight in the same direction. And equation fits as well because the exponent is 1. And if 15 videos are rented, what would be the revenue? Well, our revenue would be 3 times the 15 videos rented plus 6. And that would be 45 plus 6, which would be $51. All right, that is the end of our first day on Chapter 5, Linear Functions. There will be a Schoology exit quiz for you to do right now to see if you understand the